Yeah, so let me do a quick recap. In the last class, we looked at some basic, or we recollected some basic notions in calculus. We started with convergence, continuity, etc. Right. So first of all, we saw what do you mean by continuity of a function. In fact, it's very analogous to the continuity of a function that maps from R to R. Right. So you say that a function is continuous at a point. You take any sequence that converges to that point, the function value should also converge to the function value at that point, right? That's all. That's the definition of continuity of a function. In fact, it's continuity at x, right? When do you say that the function is continuous? It should be true for all x in the domain of the function, right? That's all. And we saw what do you mean by derivative. So the analogous thing here is what is known as the gradient. Okay. So then we looked at the analogous to second order derivative. We have what is known as the Hessian, right? It's a matrix which is n cross n matrix. And then we also looked at what is known as the remainder form of Taylor series, which is quite useful tool to know. In fact, the interesting thing about this is it gives you an exact expression or exact equation for the function f of x. In terms of course, the first and second order quantities are quite clear. You can compute it. But the second order quantity is something that you don't know how to compute. But if I know that if I can somehow control the second order quantity, then I can control the function. That's what it says. Then we looked at a similar notion for a function mapping from Rn to R. Then we looked at a few consequences of this. If Hessian is positive, semi-definite, what happens and so on. And finally, we looked at a general optimization problem, how it looks like. And then we looked at the constraint set, and we started studying the constraint set, right? So we looked at a specific form of constraint set, which is called a convex set, right? In fact, this is any set. We say that a set is convex if you take any 2 points, draw a line between them, all the points on the line should belong to the set. Okay, so this is the formal definition of a convex set. And then we saw that a ball, Euclidean ball, or any ball in n dimension is in fact a convex set, right? And then yeah, so we also looked at the set of all positive definite matrices, symmetric matrices. It forms what is known as it's a convex set. More than that, it forms what is known as a cone, right? So we also saw what is a cone. And then finally we looked at a particular optimization problem, and we realized that the constraint here can be thought of as a cone which is intersected by a circle in 2 dimensions and a sphere in general, right? So let's continue. So now we have the notion of so 2 things, right? So we looked at what is known as a convex set, and we also saw what is a cone, right? Obviously, so now the question is, why do we need to study these things, right? So let's look at some intuition. It may not be that clear in the context of optimization, but at least it will give you some idea of why we need to study these sets. So typically, we consider a function which is like this, right? So in fact, in 2 dimension or in 3 dimension, it will be like this, right? These functions are called what is called convex functions. We'll see what that means. And you want to minimize this function by picking points in a set called convex set. So convex set looks like this, okay? In 3 dimension, it will be like this, right? Think of it as a ball, right? A stretched ball or whatever. And you want to pick points from this ball such that you reach the minima, right? Now, what I can do is I can pour water into this function. So what do I get? Look at a bucket, right? So a bucket is basically a convex function, and you pour water into it. What do you get? You get a bucket full of water, and it's a set, right? Think of even a point here. I can think of it as a point belonging to this set. This set will be convex. Okay. You take a convex function, pour water into it, you get a body which is a convex body, right? And you have a convex body here also, right? All that I have to do is find this point, right? So somewhere here. Well, it essentially boils down to finding some sort of a distance between the two convex bodies, right? Optimization problem with a constraint turns out to be that. So that's why it's important to study convex sets before studying convex functions. Anyway, so this is something, it has got something to do with Lagrangian dual, which we will study later on. But we will start with convex sets. So before studying more about the convex functions, etc., so we will see how to make certain sets which are not convex into a convex set. So let's look at this kind of a set. Okay, so this is some set. So how is this convex? No. Why? You take any 2 points here, join a line, most of the points don't belong to the set, right? Therefore, it's not a convex set. So how do you convexify it? Whatever convexification means. I want to turn this into a convex set. So how do you convert this into a convex set? What do you do? How do you convert this into a convex set? All that you have to do is maybe, take this line here, connect this, and take all the points here and push that into the set, right? This particular set, right, this whole thing, right, will be your, this whole thing included, right? This whole thing will be a convex body, right? So how do you mathematically define this? Let's look at an example. Suppose I give you 3 points. Definitely, my set consists of 3 points. Obviously, it's not convex, right? How do you convert this into a convex set? Well, remember, you take any 2 points, join the line, all the points should be there. Of course, I'll join the line here. So that means all the points on this line should also be there in the set. So I have to push all those points. Similarly here, I have to push all those points. Similarly here, right? So that means all the points on the surface of this triangle should belong to the set. But what about this point here? Huh? See, this point belongs to the set, this point belongs to the set, so all the points in between should belong to the set. So this point should also belong to the set. What about this point? Same argument, right? So this point belongs to the set, this point belongs to the set, so all the points belong. So in other words, this whole region, triangle, is a convexification of 3 points, right? It's called convex hull. Just a name, you should remember this name. It's called convex hull. So how did we get the convex hull of these points? By taking convex combinations of all the 3 points. So there is a new terminology called convex combination. So what is a convex combination? We did lambda x plus 1 minus lambda y, right? That's a convex combination of 2 points xy. Suppose I give you 3 points. What do you mean by convex combination? So let's look at that. Okay. So lambda x plus 1 minus lambda y. This is a convex combination of 2 points x and y. What can you say about lambda? It's a non-negative number. I mean, it's between 0 and 1, right? So this is 0 and 1. This is also between 0 and 1. And when you add these two, right, lambda plus 1 minus lambda, you get 1. Right? Let's generalize that. So how do we generalize this? So let's do the following. Okay, so let's write this as a definition. It's clear. Given x1, you give me n points. Okay, instead of 2 points, you give n points in some Rn. Well, let me use k points in Rn. Okay, you are given k points in Rn. The convex combination is defined as how do you define convex combination? For 2 points is lambda and 1 minus lambda. So for n points, what should I do? Huh? Okay, what about 3 points? Suppose I give you x, y, z. So what should I do? I should multiply each one of them by some numbers and add them, right? That's a combination, linear combination. If I were to, what about convex combination? So how do you make the convex combination of these points? You should ensure certain properties. So first of all, when you took 2 points, the coefficients added up to 1. And all of them are non-negative, right? Lambda and 1 minus lambda both turned out to be greater than or equal to 0. Let's generalize that, right? So how do I generalize? I equal to 1 to k theta I xi. This will be the convex combination. Theta I should be greater than or equal to 0 for all I, and lambda plus 1 minus lambda is 1. That means the coefficients, when you add them, you get 1. So here also, when you add the coefficients, you should get 1. Right? This is called the convex combination. In fact, if you take 3 points and take the convex combination, you will get all the points. If I choose different theta i's, I get different points inside the triangle. Right? Is that clear, everyone? So what do you mean by convex combination? Okay. Now this leads to what is known as the convex hull, right? So let's see what is a convex hull. What is a convex hull? What is a convex hull? What is a convex hull? So you took 3 points, took the convex combination of those 3 to get the entire triangle, right? So that process is called convex hull, or the set of all points inside the triangle, including all the 3 points, is called a convex hull of those 3 points. So how do you define that? What do you think is the how do you define? Any idea? How do you define this? Yes. How do you define the convex hull? Right? How do you define convex hull? Convex hull of x1, let's look at endpoints only, or k points, is defined as, well, I have to take all possible convex combinations of these k points and push that into the set, right? That's called the convex hull of, this is called conv of this set x1 xk, which is defined as, you look at all the convex combination of these k points. So how do I write that? I equal to 1 to n theta I, sorry, I equal to 1 to k theta I xi, such that summation over all I theta is 1, theta I is greater than or equal to 0 for all I, right? So this is your convex hull. So in fact, if you take 3 points and do convex hull, you get the triangle, right? Is that clear, everyone? So this is how you do. So how do you do convexification of a general set like this? How do you do convexification of general set like this? Well, now remember, it may not be enough to take some 2 points and do convex hull. I can take any number of points and do convex hull, right? So in fact, this weird shaped non-convex set, if you want to do convex hull, you should take all possible points and do convex hull of all, convexification or convex hull of all possible points, right? Then I get this set, right? That's called the convex hull. So how do you define this? Okay, let's do this. Okay, at least geometrically you understood what you mean by convex hull, right? For weird shapes also. Let's define this mathematically. So let you take any set. Okay, so I'll take some set. Okay, so take some S contained in Rn. It's a subset. Okay, the convex hull of S is defined as, you take all possible points, you take any number of points and do the convex hull of it, right? So that gives me this set. So how do you do that? One way is you pick any number of points, do the convex hull. Are there any other ways of doing it? Huh? So what I'm going to do is the following. Okay, so I'll just give you a different idea. I'll define it slightly differently. Uh, One way is, you take this ball, right? This is a convex set, but the original set is contained within this convex set. Okay, this is also a convex set, and this convex set contains the original set S. S is non-convex. Okay, I can keep on doing that, and I take intersection of all the convex set that contains this set, right? I can do that, right? So I'll define it that way. Okay, as intersection of all the sets, let's say I'll call this sets as C's. This C contains S. This is like uncountably many intersections I'm going to take. So when I take all the intersections, I get a convex set. Or equivalently, I can say, it is all those I equal to 1 to L theta I xi such that x1 through xl is contained in S. L is any natural number, right? And theta i's are all non-negative, and you sum these theta i's, you will get 1. Well, remember what are the variables here? So you give me L, right? The number of points to pick. I take those many points, L number of points from the set. I'll take all possible convex combination. I'll get several points, right? I'll throw into the set. Remember, the L points that I've chosen can be different, right? I'll choose some other L points, do the same thing. Keep on doing that for L points. Now you are not happy with L, you give me L plus 1. I'll keep on repeating the same thing again and again and again. I'll push all the points into the set. That's the convex hull, right? But geometrically, it's very easy, right? So what is the convex hull of, for example, this will be easy, right? What is the convex hull of this? This is definitely not convex set. So what will be the convex set? All the points, right? This is the convex hull of the convex set. So for example, if this is your S, right, this whole in red will be convex hull of S. I'll write it as conv of S. Is that fine geometrically? Okay. Okay, so now we know what convexification is. There is similar thing called conification. So what do you mean by conification? Well, this is just out of interest. We may not use it anywhere. But what do you think is a conification? Suppose I give you a point. What is the conification of this point? Huh? Convexification, where did we start? We started with convex combination. Then we took all possible convex combination to get convex hull. So if I give you 2 points, what is conification? I should take conic combination. So what is conic combination? See, basically you take all possible cones that contain these 2 points and take the intersection, right? So you take, for example, this. What are the cones that are possible? So suppose this is your axis. Then what are the possible cones? See, this is one possible cone, right? There is another possible cone, and so on. This is also a cone. Straight line is also a cone. Why? You take any point on the line, scale it, you will get a point on the line, right? So it's a cone. So of all possible cones, if I take intersection, what do I get? I get this straight line, right? So straight line is basically a conic hull of a point. What about 2 points? Suppose I have this. Let's say I have 2 points here and here. What is the conic hull of this? Yeah, so basically I have, this is conic hull, this is conic hull, and all the points between them is also, right? This is conic hull, right? I will leave this as an exercise. So conic hull, so as a reading exercise. So you should read and reading exercise. Okay. You will go through it, and those who will scribe these notes, they are going to read about conic hull and they are going to scribe that as well. Okay, slightly more I wouldn't say challenging, but more work. Okay. Yeah. So any question? Any question so far? No? Right? So what we will do is we will revisit some of these again whenever required, but let's move on to convex functions now, right? Before that, okay, so I have to give one more example here, right? Example of a convex set. So example, set of all x such that A transpose x is less than or equal to B. What is this set? What is this called? Remember, what is A transpose x equal to B? Set of all x such that A transpose x equal to B. What is that? Hyperplane, right? So what is A transpose x less than or equal to B? Huh? It's all the points on the hyperplane and below the hyperplane, right? It's called a half space. Did I mention that before? No? Okay, so this is called a half space. Okay. Well, why is it called a half space? So if you have this, it's all the space below that hyperplane. This is an everlasting hyperplane. So, well, by definition, hyperplane means everlasting. Okay. So it's half the space, right? So below it. Do you agree? Yeah. That's why it's called half space. So is this a convex set? Well, intuitively you see, you take 2 points here and maybe here. I take all the points in between. Of course, it's there, right? So is this a convex set? Yes. So how do you prove that? You take 2 points, right? Let you take 2 points. Maybe I'll call it as x and y belongs to. I'll call this as h, right? Then I have to check if lambda x plus 1 minus lambda y, whether this belongs to the set or not, right? So how do I verify? I have to ensure that A transpose times this convex combination is less than or equal to B. If I show that, then it belongs to. That's trivial, right? So lambda A transpose x plus 1 minus lambda A transpose y, but this is less than or equal to A transpose x is less than B. A transpose y is also less than or equal to B. You will get B, right? So A transpose times the new point is less than or equal to B. Therefore, this implies lambda x plus 1 minus lambda y belongs to C. Sorry, belongs to H. Right? So that proves that half space is a convex set. Okay. Now, another small result. If I take two convex sets, right, let C1, C2 subset of Rn be convex sets. Okay, I have two convex sets. Then what can you say about C1 intersection C2? Of course, this is a subset of Rn. Is this a convex set? Huh? Let's verify, right? So how do you prove this? It's easy. You take 2 points. Let x, y belongs to C1 intersection C2, right? I have to show that convex combination of these 2 points also belong to the intersection. So what do you mean by that? It should belong to both S1 and C1 and C2, right? That's what I have to prove. So since xy belongs to both, it should belong to C1 and it should also belong to C2, right? So this implies xy belongs to C1 and xy belongs to C2. What does this mean? See, remember C1 is a convex set, right? So convex combination should also belong, right? Lambda x plus 1 minus lambda y belongs to C1 and lambda x plus 1 minus lambda y also belong to C2, right? Because both are convex sets. So now I'll call this point as some z lambda or something. So Z lambda belongs to C1, Z lambda belongs to C2. What does that imply? Z lambda belongs to C1 intersection C2 because it belongs to both. That proves the result, right? So it means is a convex set. In fact, I can take any number of intersections, right? A small question to think about. If I take infinite, countable infinite intersection, whether it will be a convex set. Second question, if I take uncountable intersection, so whatever, you should figure out what do you mean by uncountable intersection. You should think whether it will be a convex set or not. So think about this. Okay. Finite, it's clear, right? Induction will tell me that if you give me a billion convex sets and I take intersection, definitely the intersection is a convex set, right? This itself is enough. Okay, now let's use this. Okay, so this, let me introduce you to something, okay, so called linear. Did I introduce you to linear program? Okay, so what is a linear program? It's something like this, okay, minimize A transpose X such that maybe I'll use a different C transpose X subject to A1 transpose X less than or equal to B1, A2 transpose X less than or equal to B2, and so on, AN transpose X less than or equal to Bn. There are n constraints. One linear function, C transpose X, it's a, what is C transpose X? It's a hyperplane, right? Okay. Now I want to solve this problem. So of course I won't tell you how to solve this problem, but let's try to see what kind of a constraint is this. Well, where do you get these problems? Well, there are so many applications where mainly in computer science where you end up having these kind of constraints. But let's try to understand what these constraints mean. So what is A1 transpose X less than or equal to B1? That means you should collect all those points such that A1 transpose X less than or equal to B1. What does that correspond to? All the half space, right? Everything. What is A2 transpose X less than or equal to B2 correspond to? Right? What does intersection correspond to? Right? A3, A4, maybe like this, right? Not necessarily, but you'll get what? You get some sort of a polygon, right? Well, it's a polygon in n dimension, right? So in 2 dimension it's easy. 3 dimension itself it becomes complicated to imagine, but still you can imagine, right? N dimension you cannot imagine, but it has so many surfaces or faces, and they intersect, and you have this, right? So this is the constraint set. Now, is the constraint set convex? Yes or no? Why is it convex? Hint is whatever, we just now proved something, right? What is that called? Intersection of convex set is a convex set. So it's intersection of hyperplanes. All the half spaces. All the half spaces are convex, so the intersection is also convex. Okay. Now imagine, okay, in 2 dimension you imagine a polygon. Okay, maybe a pentagon. I have to pick a point in the pentagon that maximizes C transpose X. C transpose X is a plane, right? The height will give you the value of the function. Now, what do you think is the optimal solution? Can you guess? Of course, I won't prove anything mathematically here, but I'll give some intuition. That's all. You imagine a board placed like this and a big pentagon, right, as your constraint. So all the points inside that pentagon. So what do you think is the solution? Yes, any idea? Imagine. Can it be a point somewhere here? Let's argue that out. So can it be a point here? Huh? Yes or no? See, I have some epsilon of room around that point, right? I can still be inside the constraint set, right? The moment you are inside the constraint set, that point is called a feasible point, because that's a feasible solution, right? So at least the constraints are met. So now you have some epsilon of room. Can I move in that epsilon of room and increase my objective, C transpose X? Is that possible? Obviously, right? I can move in the direction of C, right? C transpose is some vector. I can move in that direction and still get a positive, or if it is minimization, then I'll move in the direction of minus C, right? You agree? And still decrease. So this cannot be a point. Same argument applies to any point you pick here, right? Inside. Do you agree? So what do you think is the solution? Where the solution lies? On the surface, right? On the hyperplane, this intersection. Now the second question is, can this point, the solution be on this point here? Can it be a solution? Huh? So now here I can move here or here, right? Two directions. But in general, you'll have more whatever flexibility. But now, given this, do you think this can be a solution? Not really. I can move in this direction or this direction. One of the directions will give me positive inner product with C. So I'll move in that direction, right? So now what happens? Well, these are all, none of these points are solution. Of course, solution should exist, right? So what are the possible points? These points are called extremal points. Okay, only these points can be the solution. Well, which one, you have to figure out, right? So you have to come up with an algorithm. And how many of you have heard of simplex algorithm? Simplex linear program? Huh? Heard of it? Yes or no? Can you raise your hand? Don't worry, I won't ask any question, but have you heard of simplex? Never? Okay, so it's a pretty famous algorithm for finding out solution to linear program. So essentially, simplex, what it does is it's an algorithm to find these corner or the extremal points, which is a solution, right? So that's what people do. Anyway, so this is not my intention was not to show that the extremal points correspond to the solution, but just to give you an intuition about the half spaces, intersection, and so on. It's quite useful, right? Geometrical view. Okay, so now we have intersections, which intersection of convex set is a convex set, and we used some illustration through linear program, and also it introduces you to linear program. Okay, so let's move on. Now let's start looking at what is known as convex functions, right? So what are convex functions? How do you define this? Convex functions. Convex functions look like this, right? So you have something like this, right? This is your convex function. It's downward and it goes down, and then you have one minima here, right? Well, not necessarily one minima. You can also have a bucket kind of a thing, which is also convex. Let's look at what are the properties of this, right? So towards that, let's consider 2 points, right? So one point here. Okay, let me call this as x, right? Maybe I'll call it as x1, and the other point here, okay, x2, right? Now I'll join a line between them, okay, right? I can join a line. So this line is above the function, right? No matter what, you pick this point and this point and draw a line. All this line joining between the 2 points always lie above the function. How do you mathematically write that? So I have to consider a point here, right? For example, I take a point here, right? So the height of this point, right, is always above this point, right, on the function. So for example, this is your function, right? Now the only thing is I have to figure out what this point is, right? What is this point? Convex combination of, so basically it's all the points between, right? It's convex combination of x1 and x2. So how do I write? Right? Fine. What is this point? It's f of that, right? So let me call this as f of lambda x1 plus 1 minus lambda x2. This is the height. Now comes the question. So what is this point, this height? What is this height? Huh? See, I'm taking this height, and it's a linear combination of the heights, right? So this is nothing but lambda f of x1. See, height of this is f of x1, right? So this is f of x1. This is f of x2. So it's convex combination of f of x1 and f of x2, right? That gives me this point, right? This is fine. Okay. Now what is convexity? This height is more than f of lambda, whatever, right? So this clearly says f of lambda x1 plus 1 minus lambda x2 is smaller than or equal to f of lambda times f of x1 plus 1 minus lambda times f of x2. Well, this should be true for any x1, x2 that you pick in the domain of the function and any lambda between 0 and 1, right? So that is the definition of a convex function. Shall we write the definition now? So intuition is clear, right? So we can write the definition. So definition, we'll write a general definition, okay? So we say that f, which is mapping from Rn to R, is a convex function if you take any 2 points in the domain. So for every x1, x2, okay, I'm going to use a notation now, okay? So I'm going to use the domain of f. That means all those points over which f is defined, okay? If I want to basically I have to avoid this, what should I do? I'll redefine my function in such a way that my new function is equal to the old function in the domain. Otherwise, it's infinity. Okay, I can do a lot of such things, but right now I'll write it as is. Okay, domain of the function lambda belonging to 0, 1 for any x1, x2, and for any lambda belonging to this, f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Right? This is the definition of, this is how you convert geometry into Greek and Latin, right? Called math. Okay, so we have this definition. Let's look at some of the consequences of this definition. Okay, so what are the consequences? Okay, so let's say, what does it imply? Consequences are, yeah. Okay, so what I'm going to do is you take a function to R. You have this function be convex. So I'm taking a convex function to begin with. Think of always convex function will be like this. Okay. Now we take 2 points. Okay, so let's say let xy belong to domain of f. We take 2 points x and y. Okay. I'll take convex combination of these 2 points. One way of writing that is lambda x plus 1 minus lambda y, right? Or I can write it as y plus 1 minus lambda x, right? You agree? Lambda x plus 1 minus lambda y, or x plus, or y plus 1 minus lambda x. Do you agree with that? So f of, I'll take this. Okay, I'll write it as is. This is the convex combination, right? But what is this? This will be y plus, sorry, this is f of y plus, because y gets multiplied by 1, you get y plus lambda times x minus y. Do you agree with this? Right? By convexity, what do we have? This is less than or equal to lambda times f of x plus 1 minus lambda times f of y, right? Do you agree with this? Is that correct? lambda x x minus y. Yeah, this is correct. Okay, fine. Now let's subtract f of y. So all that I'm trying to do is see what the derivative is or the gradient is, right? So what should I do? It's like f of y plus, if lambda is very small, right? So I'm moving in the direction of x minus y by a small quantity and looking at what the function value is, right? If I subtract by f of y and divide by a small quantity and take that limit, I get the derivative, right? That's what I'm trying to do. So let me subtract f of y on both sides. So what do I get? F of y plus, is it lambda times x minus y is less than, okay, I'll subtract f of y on both sides. This is less than or equal to, what do we have on the right hand side? Lambda f of x plus f of y. I subtract, so this times this f of y is times 1 is f of y, and I subtract f of y, so they cancel. So I have minus lambda f of y, right? So it's lambda times f of x minus f of y, right? This is lambda times f of x minus f of y. Okay, this is what I have. Now I'm going to divide it by lambda, right? So what do we have? F of y plus lambda times x minus y minus f of y divided by lambda is less than or equal to f of x minus f of y. Is that okay? Is that okay? Now take lambda to 0. I can do that, right? So it's any lambda between 0 and 1. So I'm going to take lambda to 0 from right. Okay. Of course, I'll ensure that my lambda is between 0 and 1. And my lambda, I'll take it from here to 0, right? I'll take such a sequence. Now, what happens to this left-hand side? Can somebody tell me? See, I started y and I'm going to move in the direction of x minus y by lambda, right? I'm going to look at the value there and value here and look at the difference. But I'm going to shrink that x minus y length, right? So by multiplying by lambda. So what do you think you get? I get the derivative, which is the gradient, in the direction of x minus y, right? So how do you find the derivative in the direction of x minus y? What is the gradient in the direction? How do you find that? What is that called? Huh? What is the component of x in the direction of y? Okay, you should answer that. What is that? How do you compute that?
Projection.
Huh?
The projection of that.
Projection, right? So what is, how do you get the projection?
By the inner product.
Okay, what is the inner product in Rn? Typical inner product. X along y is x transpose y, right? That's the inner product, right? So gradient along x minus y is what? X minus y transpose times the gradient, right? So this implies x minus y transpose times the gradient of f at y is less than or equal to f of x minus f of y. So this implies f of y is greater than or equal to, f of y is less than, no, I think I should write it in terms of f of x. F of x is greater than or equal to f of y plus x minus y transpose gradient of f of y. This is interesting, right? This inequality. Now let's compare this with the remainder form. Okay, x and y are 2 points. Let's look at f of x around y. So what is the remainder form? Let's see the remainder form now. So f of x around y, right? So it's f of y plus x minus y transpose times the gradient of f at y plus, I stop at the second order, x minus y, oh my god, x minus y transpose, what else? The Hessian of f at some point x star, I don't know what that point is, times x minus 1 by divided by 2, right? Where x star is some point between x and y, right? You take some point x and y, x and y. I don't know what that x star is, but this is true. Now, see, f of y plus x minus y times the gradient. So it's the gradient in the direction of x minus y plus higher order term. What do we have here? F of x is greater than or equal to f of y plus x minus y transpose gradient of y. You stop there, you get an inequality, right? F of x is greater than. That means if by adding this quantity, I get equality. By removing that quantity, what do we get? The function value, I mean, the right hand side goes down, right? So that means this has to be positive, right? And it does not matter what x and y you pick. Do you agree? You pick any x and y in the domain, it's true, right? What is that called? This implies x minus y transpose the Hessian of f of x star x minus y is greater than or equal to 0 for every xy in the domain of f, right? And for some x star in xy, right? This is true, right? You agree? Now, if I ask the reverse question, suppose, okay, well, what does this mean? Suppose this is true for, so any xy, right? That means any x minus y, it's true. That means you take any vector v, v transpose Hessian v is greater than or equal to 0. So what does that mean? The Hessian is positive, semi-definite, right? So now, what can you conclude from this? Okay, so I'll pause here for some time. So what can you conclude from this? We started with convex, right? We showed that for convex function, this is true. But we didn't show that if this is true, then f is convex, right? Did we? No, we didn't, right? But we showed that if the function is convex, this is true, right? But this can be true. If this is true, what else can be true? So this is also true, right? F is convex, that implies some inequality, that implies that it's positive, semi-definite. So that means if the function is convex, then the Hessian should be positive, semi-definite, right? Is that fine? Okay, so if f is convex, implies what? The Hessian is positive, semi-definite. Now the question is this true? If Hessian is positive, semi-definite, can you conclude that it's convex? Yes or no? That means if Hessian is positive, is semi-definite, definitely this is true, right? This inequality is true. But the moment this inequality is true, if you can prove that it's convex, then we are done, right? So now, obviously, the question that we will ask is, if f of x is greater than or equal to f of y plus x minus y transpose gradient of f at x, this implies f is convex. Or sorry, implies f is convex, right? So this implies positive semi-definiteness. So that's what we asked for. F is convex, this is positive definiteness. If the Hessian is positive semi-definiteness, is it convex? So that means if f is, the Hessian of f is positive semi-definite, this inequality is true. If that implies f is convex, then we are done. Okay, now can somebody tell me the idea? So what should we do? We should prove that this is convex, right? How do you prove that this is convex? How do you prove that this thing is convex? Huh? What is it that you will do? Any idea? Okay, so I'll give you a hint. So essentially, what is convexity? You have x, so you have 2 points. You take the convex combination. The function value is lower than the convex combination of the function values at the two extremes, right? That's what it says. Now, okay, I'll hint. So I can do this, right? Take 2. Now I can these two inequalities are true, so I can do some sort of a linear combinations, and now the point here is that you have to choose x1 x2 appropriately. Then I can do lambda times f of x1 plus 1 minus lambda times f of x2 is greater than or equal to lambda times whatever, right? So I can do all those funny things. But now if I want to get, okay, so now let me modify this a little bit. Okay, I'll call this lambda here. Okay, f of lambda. So what do I get? Lambda here and lambda here, right? Now if I multiply by the first equation by lambda and the second equation by 1 by lambda, I'll get f of x of lambda itself on the left hand side, right? Is this did I do this correctly? No, I think I should do the other way. Sorry, I should do x1 x2. This is fine. X1 x2. Maybe y1 y2 I can do lambda here. Okay, phi lambda is a convex combination of x1 and lambda some y or something. Now when I take the linear combination, I'll get f of y lambda on the right hand side. Left hand side you should carefully choose so that you get that inequality. That's the idea. Okay, so anyway, so I will leave this as a gap, so we will revisit this proof in the next class. So essentially what we are going to prove is that result in the next class, I mean not the result, the proof of the result. Next class. So what is the result? If the Hessian of f is positive semi-definite, implies f is convex. So that means positive semi-definiteness is a both necessary and sufficient condition for convexity. Why is it important? Let's maybe look at one example, or maybe we'll look at some examples, right? So let's look at e power x. See, what does that translate to in one-dimensional case? What do you mean by Hessian of a one-dimensional function? What is Hessian of e power x? Huh? What is Hessian of e power x? Huh? E power x itself, right? Can e power x be negative? No. What does that imply? That function is convex, right? So this is convex. Okay. Okay, let's look at this. What can you say about this? Log of 1 plus x. What is the Hessian? Hessian means second derivative, that's all, right? First derivative is 1 over 1 plus x, second derivative is minus 1 over 1 plus x whole squared. So for x greater than 0, what do we get? Negative, right? If I take negative of this, what do we get? Positive. So is convex. Well, if f of x is convex, minus f of x is called, see, f of x is like this, minus f of x will be what? If this is 2, it will be mapped to minus 2. If this is let's say 1, it will be mapped to, so you'll get, what is this function called? Hey, if this is convex, what is this called? Optics, huh? Concave, right? So, okay, so that is also an important point. If f is convex, then minus f is concave. Well, I defined concavity as minus of a convex function, right? Okay, so this is clear. So it's very easy to verify whether a function is convex or not by looking at the second derivative or the Hessian rather than going by first principle, right? F of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. You know, instead of verifying that inequality, you can just take the second derivative, which is like very straightforward, right? Okay. Any questions? Any questions? No? Okay. One more small observation. So if f of lambda x plus 1 minus lambda y is strictly greater than, well, it should be less than, right? This lies below, right? Strictly less than lambda f of x plus 1 minus lambda f of y for all lambda. Well, I should not take lambda equal to 0 or 1. Okay, so I should exclude that. And for all xy in the domain of f, then f is called strictly convex. That means you cannot have a bucket and then call it as a convex, strictly convex function. It's a convex function, but it's not strictly convex. Why? So let's look at one function like this. Right line. Is this convex? It's a bucket, right? It's a convex function for sure because you take any 2-point join, the function lies below. But what about this point and this point? Right? I draw a, okay, so I take this point, I take this point, draw a line and take this point. This height of the function is same as linear combination. So it will be an equality, right? So that means this is not strictly convex because it flattens out, right? If it's not like this, why is it important? Can somebody guess? Since we are studying optimization, why do you think this is important? What is the minima of this function bucket? All the points here, right? There are uncountably many points which are minima. What about strictly convex? Unique, right? The local optimum is also a global optimum and it's unique, right? That's why these kind of functions are important. So we need to study what is known as strictly convex function. So we will see what are the consequences and so on. We will prove that there is only one minima for this. So there are so many interesting things that you can do. Okay, once we study this, we will look at an algorithm called gradient descent, simple algorithm, and a few other algorithms to understand how things work here. And then we will look at, we'll put constraints and see how to handle those constraints. That leads to duality theory and KKT and so on. And eventually we'll look at other optimization problems as well. Okay, with this I'll stop. Yeah, thanks.